Now we have Doron Zarchy. He is the head of research at Phoenix, a company pioneering fully homomorphic encryption for Web3 applications. Doron's talk, High-Throughput Universally Composable Threshold Cryptography, will explore new breakthroughs in scalability and security for decentralized computation. Please welcome Doron Zarchy.
Great point. Okay. I'm representing the paper that we had 3 weeks ago in CCS. This is more of like a sort of academic type presentation about threshold decryption FHE. This is a joint work with my co-authors, Guy Ziskind, Chris Peckert, and Max Leibovich. Okay, so Nigel gave a great presentation for what FHE is and what decryption FHE, threshold decryption FHE is. I'll give a very short introduction for this, just to be realigned on this. So FHE is a special type of encryption scheme that allows to perform homomorphic operations over encrypted data while keeping the data private. So a typical scenario would be someone who encrypts the data, send it to the server. The server just perform a bunch of homomorphic operations, and then at some point send the ciphertext back to the user, where we assume that the user has the secret key to open this ciphertext. So and send it back and get the message. And in many cases, we have more than one owner of data. We have multiple owners. So in this case, we can share the secret key across multiple parties. And so each get its own secret key. We can use any type of secret sharing scheme we want. And then each party perform, then we have the same scenario. The user, for instance, in blockchain, just encrypt the data, send it to the servers. The servers perform homomorphic operations, and then send the ciphertext, the resulted ciphertext, which we assume that should be is the same for all partial decryptors. Each one performs partial decryption operation. So this is, again, it depends on what scheme we want to have, but they do it. And then it depends on the decryption scheme. It can be, for instance, honest majority, so we need only honest majority of these parties to act correctly, or we can have like even super majority or dishonest majority and dishonest majority. We can actually have just only one honest person, one honest party to perform this, but we'll get it back. We'll get back to this. A typical scenario of threshold FHE would be sealed bid auctions. So you can think of a scenario where people want to buy some product, but they don't want to reveal the prices that they are willing to bid. So what they do, they simply encrypt their bid and send their bid to the server. The server then gets a bunch of ciphertexts where each encrypts their bid, and then the server just applies a max function, and this outputs a new ciphertext, for which the server still doesn't know what it contains, but it contains the highest bid. So then it sends this ciphertext to these partial decryptors, who then decrypt it and get the result, which is the winning bid, while keep all the other bids private. Another scenario could be hospitals and patients. So hospitals clearly wants to keep their patients' data private, but sometimes they want to perform some, let's say, statistical function across all the patients, across all the hospitals. So for instance, they want to know like the average number of people with certain blood type, or anything you can think of. So how can they do it? They can, again, just encrypt the patient's profile data, send it to the server. The server now gets, let's say, many ciphertext, and then it applies some statistical function, for instance, average, and it gets a new ciphertext which encodes the average of all the people with some certain blood types. And then these decryptors can decrypt it and get a result. So note that if we do it like naively with MPC, it would cost a lot, and the communication cost will be very high. But using FHE, it really reduced the communication cost, because the communication is just sending this ciphertext to the server, and then the server sends the ciphertext back to the decryptors. So the communication is very low, and this is actually independent of the computation. So these two examples exemplify that threshold FHE is actually, in some sense, it's equivalent to MPC with very low communication complexity. This is why it's so strong, and this is why we try to tackle this problem as Zama tried. Okay, so now we'll get a little bit more technical. So FHE is based on LWE problem, all known FHE schemes based on this. So LWE encryption scheme is LWE ciphertext is a pair of A and B, where A is a random vector and B is A times the secret key subtracted from, B is A times the secret key plus the scale message plus the noise. So here this small picture of this plain text, how it looks like. So the message, the plain text, occupies the most significant bits, and the noise occupies the least significant bits, so they don't interfere with each other. So in this case, when the decryptors gets this plain text of message and noise, they can easily just truncate all the bits that corresponds with the noise and get the message. In order to decrypt it, the decryptors only need the ciphertext and the secret key. So they compute this formula, which is A times the secret key subtracted from B, which then they get, this is for a single decryptor. They just get the noisy message, and the noisy message, as I said before, can be easily transformed, or the noise can be easily extracted from the noisy plaintext to get the message. And when we have multiple decryptors, then since this function is linear, we can simply replace the secret key with the shares of the secret key, and the partial decryptors perform the same operation, but then they get the noisy plaintext. The problem with the noisy plaintext is that when the partial decryptors see this noise, when they see this, this exposes, this is actually a very sensitive part of the encryption, because when they know what the noise is, they can if one of them is an attacker, they can actually attack. They can attack the scheme and recover the entire secret key. So we don't want that each of these partial decryptors will know the secret key. We just want them to know their share of the secret key, which does not reveal what the secret key is. So we just knowing the noise reveals a lot of information. We always want to keep it secret. This is why noise flooding exists, as I just reiterate what Nigel presented. So here, noise flooding is just an additional noise term. The parties agrees on this noise term beforehand in the offline phase, and each one of them gets a share of this large noise term. And when they partially decrypt it, they do the same as we saw before, except that they also add shares of this large noise term. So when they decrypt it, they get this noisy plaintext plus large noise term. So it looks like this. And this noise should be very high to statistically mask the small noise term. But it cannot be too large, because then it will interfere with the message and we'll get decryption errors. The problem is that noise flooding comes at a high cost. In order to have enough room for this large noise term, we have to have large modulus. And large modulus in LWE also forces us, just because of security reasons, we have also to use large polynomials, and all these large parameters makes the entire scheme slower. Specifically, the homomorphic operations become slower. And this is a heavy cost that needs to be paid for the entire scheme. So the entire scheme will have this problem. So what prior works have been doing, they either did it and pay the price, and which is slower computation, or they use a smaller noise term, not so large, but then they couldn't have like simulation security, so they had to reduce it to game-based security, or they used some unusual trust assumptions, such as some server knows the secret key. And the state of the art that was presented in 2023 by Nigel and other people was presented this new technique called swish and squash, which allowed to use a smaller modulus, which improved by a lot all the previous works. But the problem is that it required bootstrapping, which is slow, which is a heavy operation, and they also used large modulus. So it was much better than all the previous works, but it was still relatively slow. So what we try to do is to completely avoid this noise flooding because of this heavy cost. So in order to do it, we used costume MPC called MPC rounding, and used offline online machinery. So we also used some pre-computation in order to allow this. So our FHE decryption protocol is actually just a variation of what we just saw, where so this is the noisy plaintext. So the decryptors receive a ciphertext, and each partial decryptor also has a share of the secret key. So what do they do with it? The same as we saw before. They simply multiply the share of the secret key by A and subtract it from B to get the share of the noisy plaintext. But then, instead of revealing this noisy plaintext, which reveals the noise, they do MPC. They perform MPC, and this MPC is used to extract the noise and to share it among the decryptors. So this is so they jointly compute this, and this will be the focus of what I'll talk in a minute. And given that they do it, they can have, since this linear, this shares, and this equation is linear, they can simply compute the shares of Z is the noisy plaintext, the shares of Z minus the shares of E to get the shares of the message. This message is shifted, but they can easily reshift it to get the real message. And when just another remark, after they compute these shares of the message, they need to reveal it. But again, this share just contains the message, and there's nothing sensitive about it, so it's fine. Okay, so now I'll get like to the core of the technical challenge, is to do this MPC of what we try to do is to compute the shares of this noise based on the noisy message. So actually, I'll just show you the first attempt, which is actually very easy, which just used masking. So in order to compute these shares of the noise, so the parties cannot simply share. They cannot open the noisy message. So what can they do? They can open a mask of this noisy plaintext. So what do? They first, before the encryption starts, before anything starts in the pre-computation, they agree on some randomness R, and they share this. And then each party has a share of this R, and they compute this masked noisy plaintext, basically the share of Z plus R. Then when they open this sharing, they open only the noisy part, which is basically the shares of E plus R. But since R completely masks E, they can open it. So everyone knows now what is E plus R. Now this is public. Z prime is public. So then they can compute each one locally Z prime minus the shares of R, which is the shares of the noise. So this is it. So this is actually very simple. Everything we did is just adding some randomness, shares of randomness, opening and removing this randomness. That's it. So actually this is very simple, but there is one caveat, is that it doesn't work always. Because on the third step, Z prime minus shares of R can be smaller than 0. We call it overflow. So in the first case, this works, but in this first case, which is when Z prime is larger than R, this works, but when Z prime is smaller than R, it doesn't. For this, we need to add some correction term. So what do? If this Z prime minus R is smaller than 0, we add the correction term. We just add, I write it 2 to the L because it's the noise takes L bits. So it just, regarding the modulus, everything here is taken modulus 2 to the L. So if you take the modulus, then even if you add this term, you get the same value. So you add this 2 to the L times the shares of U, where U is an indicator whether we had an overflow or not. And this value, whether we had an overflow or not, is a sensitive data. So we need basically to do MPC just for this. So we just want to check whether there was an overflow or not. So, and given that that we have this value, this entire protocol is sound. So this protocol does not leak information and is correct. So in the other slide, I'll just want to show you how we compute this sharing of U, which is whether we had an overflow or not. So U is equal to this equation, inequality, whether Z prime is smaller than R. Z prime smaller than R is equal to Z prime minus R smaller than 0. So, and this is equal to the function we call LTZ, which is less than 0 of Z prime minus R. So if Z prime minus R is less than 0, we get 1. If Z prime minus R not less than 0, so it can be equal or larger, it will be 0. So in order to do an MPC for that, we just open this function into a lookup table. So we have here, this is the table. R is already determined. I remind you, I just want to show you. R is determined in the pre-computation. here, but R is secret. I mean, R is secret and their share is secret, but it's still there. So we use some MPC in the pre-processing to just compute this table, and we compute the shares of the output of the function, which is 0 or 1, for every possible Z prime. So Z prime, for instance, if there are 3 bits, there will be like 2 to the 3 cells here in this table, and it will be either shares of 1 or 0. And then when we get Z prime, we can simply evaluate it. So each party gets Z prime, which is public, and can apply it to the table, to their table. So each applied to his own share. So it would look like this, basically. So each party has their own share. The shares can be either additive or Shamir secret shared or whatever secret sharing you want to use. The problem is that the number of the size of this table can be huge, because for 3 bits, 3-bit noise, it will be like 8 cells. But if we have, let's say, if we have 64 bits of noise, this table, the size of the table will be 2 to the 64, which is prohibitive. It's too large. So in order to in order to address this, we use a hierarchy of tables. Basically, we just use two levels hierarchy. So what we do is we decompose Z prime into digits and R into digits, and then we showed that the following equation holds, that less than 0 LTZ of Z prime minus R is equal to LTZ of the weighted sum of sign tables. So now we use another creature called sign tables, but these sign tables are small. So LTZ of large table is equal to weighted sum of small tables. So in the pre-processing, we'll need to build all these tables, and in the online phase, we'll need to evaluate Z prime on these tables. Now here in the pre-processing, we'll build, let's say, D or many small sign tables, where sign is basically the function that just gives you the sign. So the function gives you -1 if the output is negative. It will be output 0 if the output is 0, and will be output 1 if the output of the sign, if the output of xi minus ri is positive. Then when this was computed in the pre-computation, but now after we get the ciphertext, we decompose actually the masked ciphertext, the masked plaintext Z prime. So I remind you, we get a ciphertext, and we then perform partial decryption, and during this, each one sees the noisy plaintext. So the noisy plaintext is decomposed into digits. It should be Z prime, I don't know what, but it should be Z prime 1 to Z prime D, and evaluate each of these on these tables and get values like shares of -1 or 1, but these are just shares, but this is fine because it's linear, so all the sum and the linear combination holds. And then we take the weighted sum, and the weighted sum is the index that we will apply in another table, in the LTZ table. But now the LTZ table, it's much smaller, much smaller. So, for instance, the size, if we had this, if the original size of the table was about 2 to the 64, let's say 2 to the 60, now the size of this new LTZ table will be like 2 to the 8 or something, much smaller. And we can evaluate this index in this new table, and we get the value. So this completes the entire protocol. I think I'll skip the offline phase. So in the offline phase, basically we build these tables, and we also share some randomness that associated with these tables. The efficiency of this protocol is 3 rounds. So there are let's say when we don't want to have any mechanism on top of it for let's say error correction, or if we want to allow security with abort. Like the naive version is just 3 rounds. In each round we send around very, very small ring element, let's say 30 bits. And the total storage of all the tables is 1.k kilobytes. There are, like in our implementation, on our parameters, we used 7 signed tables, each of size 1024 bits, and one table of LTZ of size 256. Okay, the security of the protocol. So we showed that this is secure in the universal composability framework, and this allows us to have the flexibility to be secure in many different settings. So in the simplest case is the semi-honest, but we also allow to have honest majority with guaranteed delivery, or dishonest majority, where we have security with abort, which means that we can allow everyone to be dishonest except one, where even if there is only one honest party, it can always seize whether the other parties misbehave or not. But if they did, then we need to abort. Okay, regarding performance, we evaluated our protocol under different conditions, different ping time, number of parties, and different bandwidth. And we looked at 2 metrics. One is latency. Latency is the amount of time to decrypt a single ciphertext. And we also checked throughput, which is the number of ciphertexts that can be decrypted in 1 second. And we compared our protocol to the state of the art, which is NOACSARS, which is what Nigel presented. Under certain conditions of the network, we achieved 37x improvement in latency and 20,000x improvement in throughput. We checked the latency also across multiple different number of parties and different conditions of the network, and we saw that our protocol is basically, first, it's sensitive to the the latency of the network because we have multiple rounds. But overall, the amount of time to decrypt a ciphertext, for instance, for 10 milliseconds for a network with a ping time of 10 milliseconds, it is in the order of 50 milliseconds. We also evaluated the throughput. Actually, in throughput, we are much better. We looked again over different network conditions, over different. So each line here is a different latency of the network. We also, in each column, is different different bandwidth, and basically for very small latency, actually, even if it's 1 or 10, we can get to up to 60,000 ciphertext a second to decrypt. When the network becomes a bottleneck, then it clearly decreases. We get here it's like between 1,000, between 10,000 and 30,000 ciphertext a second. So yeah, so what we did basically is we proposed a novel protocol for threshold FHE that avoids noise flooding. We proved that this protocol is secure in the UC framework under various adversary models. Adversary models just means whether it was honest majority or dishonest majority or semi-honest or whatever the corrupted parties can do. And our evaluation of the online phase demonstrated 37x improvement in latency and 20,000x improvement in throughput compared to the state of the art. That's it. Yeah. Yeah. Yeah, this is, you're right.
Pushed everything.
Yeah, we pushed as much as we could to the offline phase. The offline phase is really the bottleneck. You're right. Actually, there are several layers to the offline phase as well, because in the offline phase we might assume that so the offline phase required to compute and create all these tables, and creating these tables we need some correlated randomness. So we need like MPC for multiplication, and for that we also evaluated, but we assume that we have triplets like beaver triplets or triplets for multiplication. So in this case, it's in the orders of magnitudes more, and also there is and this is when we even assume that we have these triplets. Computing these triplets takes much more time. I just want to say that we also need to do pre-computation for every individual ciphertext, so we cannot like reuse this randomness. Yeah, I mean, it does take time, but we assume that. But we looked at it, and it's. I don't remember now the numbers in my head. It's in the paper, but but we found that it's possible to scale it with. Yeah, I think the large bottleneck is these triplets, multiplication triplets. This is a really headache. So I think now we'll first start perhaps with TEs, but then we'll see how we are going to with this. Yes.
So actually that was related to the question I was going to ask, is in which situations are each protocol more favored? And it sounds like in the cases where you can do the offline phase and you're worried about the online phase, keeping it as short as possible, your protocol is probably better. And if you're not able to anticipate the offline phase, or the total computation is what you're looking at, then perhaps Noah's Ark is preferred? Or what are your thoughts in terms of when would you use each protocol?
That's a great question. So in our case, in our case, we try to tackle. We are a blockchain company. We build on Web3, and we want to actually. This should accommodate to many transactions per second. So like it should be adapted to or addressed for a high demand. And we assume that there is always, we need to compute on the back end all the randomness for each ciphertext. So in our case, when you assume, I mean, we didn't solve everything like with the offline phase, and so there's some ways to address it with TEs, for instance. The TEs, which we just delegate some trust, and that makes everything faster. Perhaps also, I think that if the network is not an issue, then our solution is better because also there are many rounds also to the offline phase. But if you have an issue with the network and you have and you do care about the latency, then Nox Arcs, which has much less rounds, and you less care about the computational side, then you would use Nox Arcs. Yeah.
Thank you.
Any other questions for Doron? If you're good, yeah, thank you, Doron, for that in-depth dive in today.